Okay, so what happened to the? Okay, so we talked about metric entropy ideas, and the hope was that fine. Just half the real estate is like gone. So we had the metric entropy, which is so if you recall, we can cover a set in basically balls in a particular metric, and the point is the number of balls of radius epsilon that we need is called the epsilon covering number, and so we proved the result that told us, so there was some sort of probabilistic argument, but at the end we proved this result that if you have a class of Boolean functions on a probability space, and the VC dimension is at most nu, then the covering number in the L2 norm is bounded by 2 over epsilon to the C times nu. And if you compare with, for example, covering number of the L2 ball in the L2 norm, that would be like bounded by 3 over epsilon to the D for epsilon in 0 to 1, usually for care about things when we go to 0. So that it has the same sort of scaling. So it's exponential in D dimension, and here it's exponential in nu, and polynomial in 1 over epsilon. So the thing is that the growth as a function of nu and D is the same, sort of. So this suggests that VC dimensions behave like, sorry, VC classes, although the class could be infinite, so have like uncountably many functions in it, but it behaves like a nu dimensional or C nu dimensional space. So I'm going to go through the proof. The proof was to reduce things to basically L2P Z. This is like the empirical norm. So you would reduce the problem to the empirical norm, and then use some sort of concentration inequality plus like probabilistic argument. So you show that things hold with high probability, then there exists a set of endpoints, and then you can reduce the problem to that. I'm not going to go over that. So what I want to do today is to show you how we can use this to improve the bound that we had. So again, if you recall, let's see if I have. So the point was, so these metric entropy ideas are useful in their own right, but the point was to sort of improve this bound. So we had this bound that said that if you have an empirical risk minimizer or a class whose loss function, so you have a class of functions, there's a loss class associated with it, L composed with H. And if the VC dimension is bounded by nu, then we have this bound which roughly says the excess risk grows like nu log n over nu divided by n. So this log can be like taken out. Okay, so that's what I want to sort of argue. And the argument is interesting in its own right, and it's just not just to remove the log, but it's worth seeing the argument itself. So the argument is based on this idea of chaining, and the result is called Dudley's theorem, or Dudley's integral theorem. So the setting is we have a process, a random process, which is zero mean. So this is a collection of random variables indexed by some subset T. Again, this T could be general, but we're going to restrict ourselves usually to a finite T. So the without loss of generality. So maybe talk about that later. But it's a zero-mean process. It's of Gaussian increments. If each one of these is zero mean, and xt minus xs is sub Gaussian for any t not equal to s. So these are the increments of the process. And moreover, we're going to assume that the sub-Gaussian norm, I'm going to assume that you know something about the sub-Gaussian norm. It's just similar to the sigma that we defined before, but it just measures, it's like the variance for Gaussian. It's like proportional to the variance for the Gaussian. Sorry, the standard deviation. But the sub-Gaussian norm is bounded by some constant, let's say sigma times a metric on the space t, so applied to t and s. So the point here is that, so you can think of this norm as measuring how big the deviations are. It's like a standard deviation. And this is saying that how big the deviations are is controlled by how close the indices are to each other. Okay, so it establishes a connection between the stochastic nature of the process and the like geometric nature of the set. So this is saying if you move a little bit from t in the metric row, then the process is not going to vary too much. It's sort of, it looks like continuity in a sense. Okay, it's just a stochastic form of a continuity. Sort of like uniform continuity. So the result is then this. So expectation of the supremum of xt. So it's like a theorem is about controlling the expected supremum of this process. And so the thing is that the expected supremum of this process, so the supremum of such a process cannot go too big. That's the thing. But the interesting thing is that the supremum, the expectation of the supremum is related to why this theorem to a geometric quantity, which is this either sum or it can be upper bounded by this integral. We're going to prove this, and then it's easy to see that this follows. So this is the Dudley's entropy integral. So instead of looking at just the covering number at a certain epsilon, we just look at the whole integral over all epsilon. And so this often gives you sharper results than just discretizing at a particular epsilon. And you can see the idea is sort of we look at all basically epsilonness at all these levels to the negative k, where k can actually be negative and positive. So it just goes from like negative infinity to, sorry, as infinity to 0. So basically all the radii, and then we just count how many balls we need and then sort of combine them. So is the statement clear? I'm going to show you how we use this. But it's a very interesting result, and the proof is also interesting in itself. And the result is fairly general, so it works for any process with sub-Gaussian increments, sometimes called a sub-Gaussian process. Okay? Have people seen the Dudley's integral before? Okay. So we'll go over it quickly. Okay, so let me tell you how you can actually use this to prove the result. Actually, let me come back to this later. So I don't need this slide. Let me prove it and then come back to it later. So without loss of generality, we're going to assume that t is finite. And this seems to be like with a lot of loss of generality, but it's not. So you can basically you can define this this guy to be define it to be supremum over f, such that f is a subset of t and f is finite. And then expectation supremum xt, t, and f. Okay, whenever the supremum makes sense, so this takes care of a lot of things, including measurability. When the supremum is measurable, let's say if it's or a countable set, then you can argue that this is equal to this. Okay, and whenever it's not, So it's just enough to control these because the entropy number of F, any finite subset of T, is upper bounded by the entropy number of T. So this right-hand side is not going to depend on. So it's going to be like F here, and then I replace it with T. So the upper bound doesn't depend on F. Then I take a supremum over F, and then I'm done. So we're going to like focus on finite T. So either definition, or equal to when the left-hand side makes sense. Just argue this for yourself. So T is finite. I'm going to take sigma to be 1. So this is saying xt minus xs. Psi 2 norm is less than or equal to rho t and s. And then I'm going to take epsilon k to be 2 to the negative k. And k varies in all the integers. Okay, it could be like -2, -1, 0, 1, 2, da, da, da. So this covers everything in 0 to infinity. And then n sub k is an epsilon k net of t. Okay. Right. So what this is saying is so let's jump to this. What this is saying is there is a projection from t to the net. So I'm going to take the closest. So this is like pi k of t is the closest point in nk to t. For every t, I can find the closest point in nk. That's the projection of the point into the net. And by the definition of the net, the closest point, the distance. So this is an epsilon net in metric rho. Right. So what it's saying is that the rho metric of t and the projection is bounded by epsilon k. So this is the definition of, so by definition of an epsilon k net. Okay. Does that make sense? Okay. And then if there's some kappa small, some k big, such that so let's say this kappa could be negative, such that this n kappa is t0 for some t0 and nk is the entire t. So if I increase the radius, basically if I reduce k, I increase the radius, eventually 1 point is enough. So this is the set. I can find a single point such that so this entire thing is lies in epsilon kappa. And if I make it small enough, at some point, make it small enough, this is epsilon k, the resolution is too big, I just pick every possible t. Okay, so there is some kappa and some k such that in the one extreme, the net can be just a single point t naught, and the other extreme has to be the entire t. So since the mean is 0, I have the expectation of t naught is 0. I can add it here. Okay, so you can see this thing comes out of the supremum because it doesn't depend on the supremum, and so the expectation applies to it, and it becomes it goes away. Okay, I can do this. So basically, I can measure the deviations of xt relative to this center point. Okay, so far so good. Okay. Then we have this simple chaining relation or telescopic relation. I can just write this deviation xt minus xt naught as the deviations of x at these two different projections. So I project t onto the kth net versus the k minus 1 net. And you can see because of the telescopic nature, this summation sort of basically reduces to the, what does it reduce to? you know how to. Pi k, yeah, t minus x pi kappa plus 1 minus 1, which is like kappa t, right? So this is basically, if you recall, this is just, is it equal to t? Yeah, so at that point, the net is that the t itself, so the projection is just t itself. And this is just projection of everything here would be just t naught. There is a signal. Okay, so the advantage of this is that hopefully these increments are like very close to each other, because the distance of these projections are not, they're not far away. The reason why they're not far away is because of this. So both of these are close to, these guys are close to, both these guys are close to t, right? So can I write an inequality for, let's say, what is the distance of, let's say, pi kt and pi k minus 1t? Can I bound this? The projection of t onto the kth net versus the k minus 1 net. Can I go via t to control this triangle inequality? Yeah, so this would be like rho pi kt and t plus rho pi k minus 1t and t. This is the triangle inequality, and the first one is bounded by epsilon k. The second one bounded by epsilon k minus 1. And then I can further bound this by which one is smaller, which one is bigger. I guess 2 epsilon k minus 1. Okay. So you can see the difference is tiny for large k. Okay. Why this is useful? Sorry? That's fine, yeah. So like epsilon k and epsilon k minus 1 are okay. 2 times this would be, no, it's actually a little bit bigger. Yeah, that's fine, but it's just small. So why it matters that, right, so it just follows from this idea that the process has controlled increments. Right? If t is close to s, then I can control this nicely. That's the point. So well, what I get is from this point here, so it's star plus SG increment assumption. This gives me, what does it give me? That x pi kt minus x pi k minus 1t is bounded by, sigma is controlled by, the sigma is 1. So this is bounded by 2 epsilon k minus 1. Okay, so the sub-Gaussian norm, this is sub-Gaussian norm. It's controlled by that. We'll come back to this. So if I take the supremum now of both sides of this, so supremum xt minus x naught, right, is going to be bounded by, I can move the supremum inside. Kappa plus 1 to k, x pi kt minus x pi k minus 1t. Sup goes inside. So why this is valid? Supremo of the sum versus sum of the supremo. Right. Okay. So basically, for every one of them, the t that maximizes it could be different. Whereas for the, like if I have a supremo outside the sum, I have to pick a single t that maximizes sum, right? So this is sort of clear. And then I put an expectation over everything. So the expectation is linear, goes inside. Okay. So you can see I've reduced the problem of controlling the supremum of the entire process to the expectation of the supremum of these little increments. Okay. So what is the next step here? You've seen Dudley's integral. What can we do now? How can I control this expected? So reduced is the controlling. Sup t in t, x pi kt minus x k minus 1t. How do we control this? Great. So these are sub-Gaussian with psi 2 norm bounded by 2 epsilon k minus 1 and 0 mean. But there are many of them. So how many should we? So I can bound this by the cardinality of t, right? So let's say, see if you can do better later. So bounded by root the psi 2 norm, which is this guy, right? Actually, it comes out 2 epsilon k minus 1 root log cardinality of t. Right? Is this good? Can I do better? Sorry. Yeah, 2 up to a constant. 2 epsilon k minus 1. 2 I can also absorb. Yeah, forget about it. Later it absorbed 2. But do we really need t here, cardinality of t? Right. So what we're doing is basically like as t varies, it's more like two nets. So these projections vary over the two nets. Right. So the number of different combinations are just the number of different combinations that I can get from like the Cartesian product. So only, so if you look at x pi kt and x pi k minus 1t, as t varies in t, the cardinality is at most that of n sub k times n sub k minus 1, because these pi kt and pi k minus 1t can only take values in nk and nk minus 1. Okay, so the cardinality of this set is basically, I can just do nk times nk minus 1, right? And in general, you can choose, if you've chosen your net nicely, this has to be like less than this. Okay, so this whole thing is going to be bounded further by epsilon k minus 1 root log 2 nk nk minus 1 is, so epsilon k minus 1 is bigger, right? So the size of the net can be smaller. Right? You can pick a net which is bad, which is like bigger, but you can definitely sort of make it smaller. And so let's say you have something like this here. So I can get rid of the 2 as well. Just argue for yourself that this doesn't matter here. So you get log nk, right? Just absorb it into constant. So that's the result that we get. So each individual one is like a c epsilon k minus 1 root nk, and then I have a summation, right? So if you plug back in, so you get the expectation of sup xt minus x naught is up to constants bounded by summation k in z epsilon k minus 1 root log nk. This is like 2 to the negative k plus 1. Again, a 2 can be absorbed, so you get summation k in z. 2 to the negative k root. This is the log of t to the negative k and rho, something like that. Okay. Does that make sense? So that's this result. Yeah, I'm simplifying things, just writing it as n to the net 2 negative k, just with respect to rho. And online people are okay? All good? Can you hear me still? Do you guys hear me? Yeah, okay. So that's this result. So you can see just that the basic level is just that inequality for sub-Gaussian random variables. Let me remind you what that was. Do you recall what it was? In case you don't recall. So right back here. Where was it? Yeah, so this result basically, what we used here is this one. And the sub-Gaussian, it's like this sigma is basically up to constants the same as so this sigma is up to constant the same as the psi2 norm, right? Get rid of this. Okay. So this is basically saying if xi's are the psi2 norm is bounded by sigma for all I, then expectation of max I from 1 to n is less than up to constants to sigma root log n. So that's the basic idea. It's control the sigma is a small related to the radius of these nets, and the n is also small because we're working with these nets again. Okay? So then you add them up. It's just a very simple, sort of simple, not too simple, but simple extension, I would say, of that basic idea. Right. And so we have this result, and then the integral is an upper bound on this. So if you note this identity, so if I take the integral of d epsilon from 2 to the negative k minus 1 to 2 to the negative k, this is just constant, integrating constant. So this would give me 2 to the negative k minus 2 to the negative k minus 1, right? Which is 2 to the negative k times 1 minus 1/2, which is 1/2 to the negative k. So if I multiply by 2, I get this. So I'm going to just replace this with integral, right? To the negative k minus 1 to the negative k d epsilon, and then move this inside the integral. It's still valid. And then what is the next step? Why can I have this, the next inequality? So why this is true? So over the range of the integral, epsilon is in 2 to the negative k minus 1, negative k minus 1, yeah, and then negative k, right? So epsilon is less than 2 to the negative k. And so if I, so basically I'm replacing this by something which is smaller. And so it gets bigger, potentially. And then this is just, you can see I'm just adding up these integrals over disjoint. These are disjoint intervals, and they cover the entire real line. So it's just equal to the integral from 0 to infinity, right? So that proves the, so this 2 can be absorbed into the constant. So we have shown that basically expectation supremum t in t xt minus xt naught, actually just this, let's say. Okay, let's write it like that. Adding t naught here doesn't matter because it's zero mean. This is bounded by a constant times root, basically log n epsilon. E epsilon. That's true. Sort of the simple result. So a couple of points is that if you go through the argument, you can actually prove, you can see that the same argument actually works for controlling this. Absolute value relative to a point. And then for this one, you don't need the zero mean assumption. Okay, it's already there. The only place we use the zero mean is to just remove this xt minus 1 out. But if you just work with this, you get that. And if you do a triangle inequality, you can write this as basically like up to a constant is like the supremum of the deviations. So the same bound gives you a bound on the supremum of the deviations. Again, this doesn't require the zero mean assumption. The other point is that you don't have to go all the way to 0 to infinity. So if t is finite, you can see below a certain point, we don't need to go, right? As you, sorry, yeah. If you like drop it at some point, the epsilon gets too small, you pick all the t. So if you start from, for example, from an epsilon net itself, you don't have to go below the, like delta net, you don't have to go below delta. And the upper end, you can just stop at the diameter of the set, right? You don't have to. So you can just, it's easier, more convenient to write it like this, but this is going to be like beyond the diameter is just going to be 1, so it's going to be 0, and you can see also that you don't have to go down all the way to 0. Questions? Not easy in general, but here's an example. Right. Okay. So the main point is that if you have an estimate, then you can plug that in, and you get a nice one on the expectation of the supremum of the process. Right. In general, it's not easy, but like for the finite dimensional case, we did like by volume argument. For this one, we did by like probabilistic arguments. Right. The main point is that this is a geometric property. So it has nothing to do with probability. And this result sort of connects the geometry of the underlying metric space to how big the supremum of a process can get. And you can also see like it goes the other way around. If you have a supremum of a process defined on a metric space, the expectation of the supremum actually measures how big the set is. So you can also go the other way around instead of like trying to sometimes it might be easier to compute this. And if you can find a lower bound, there's a simple lower bound called Sudoku's inequality that tells you basically something like this. So this is lower bounded. Just check it later. For any epsilon, it would be something like that. So you basically have this epsilon, there's this root, log Sudoku minoration, something like that, inequality. This is log and epsilon. So this is like the area here just is lower bounds this. The area here upper bounds it. There's a gap between them. You can just close the gap if you do more. There's something called generic chaining by Talleyrand, if you're interested. Based for Gaussian, or actually for sub-Gaussian processes. But for Gaussian processes, this gives you have to replace this integral with something more sophisticated, but that would lower bound and upper bound this guy up to constants. And it's a very interesting sort of quantity but in any case, sometimes this is easier to compute actually, the expectation of the supremo. So you might use it to get an upper bound in the covering number. Yeah, double check. So question. Okay. Practice, what could BT besides real numbers or natural numbers? So in general, these are very useful if you apply it to function classes. We're going to use the sort of, I'm going to show you, you can use this to control the Rademacher complexity. So the processes that are indexed by functions, basically. So you can control the supremo of empirical processes. We're going to see a very example shortly, but basically that reduces to not real numbers, but T subset of RD or Rn. These are complicated sets, so it doesn't have to be just a univariate index, or it could be, but T could be also a function class. But for us, because the functions are reduced to the restrictions on an endpoint set, basically we reduce to subsets of Rn. Okay, we'll see an example shortly. Sounds good? Let me go to the next slide and talk about how you prove it, and then you can ask your question if you're not satisfied. Yeah, okay? Sounds good? Can I? Okay, so let's go see how we can actually now use. So I'm going to combine this with the Dudley's integral to prove the result. So if you, yeah, unfortunately I don't have it. Maybe I have it actually here. Yeah, okay, fortunately I have it. So there is this generic bound that if you effectively proved, if you go back through all the arguments. I'm trying to put them in the lecture notes, but if you just track all the things that we did, we actually proved something like this, that if you look at the ERM estimator, and if this F is a superset of the loss function class, it's symmetric. The symmetry we can just drop. We can show that it's not necessary. One bounded function class has to be bounded. Then the excess risk is controlled by this Rademacher complexity, which is an upper bound on basically the expectation of the supremo of the empirical process, if you recall. So this is an upper bound on bound on P minus PZ, if you recall, F. And then plus this part, which is the deviation that you have to pay to prove a high probability bound. This comes from the bounded difference. So all the things that we actually did was to sort of get progressively more refined control of this Rademacher complexity. Okay, so what we used before was, if you go back, we basically use that sub-Gaussian maxima property, but just once. Now we have a more like refined version of it. We can apply that and then get a better bound. So applying this, so basically we say that we can control this for if the function class has VC dimension nu, then that the Rademacher complexity is bounded by root nu over n, and you can see this sort of gets rid of the log here. So it cleans up the result. The root nu n divided by root nu over n, and then this is the price that you have to pay to get a high probability bound. If you have like if you want an expectation bound, you can have the expectation. This is up to constants. Actually not, yeah. So the expectation, you'll recall, is just the expectation for the expectation. This part is enough. So if you do expectation over the randomness in the training, this would be up to constants root nu over n. So you don't have to pay that extra price. There's a very clean result says that on average, the excess risk is controlled by root. Something which looks like a dimension, which is the VC dimension divided by n. Okay, the statement is clear. So the only thing I have to do is now to control this, show you how we can use that. Yeah, so this is just to remind you how the sequence of arguments for that generic idea goes. Let's forget about this. Oh, okay, actually, I don't think. Yeah, I'm going to skip this slide. The R ABS is the same as R. So this is going to be equal to expectation. There is some sort of expectation here as well. Sorry. This should be expectation. The expectation over Z. So this is going to be expectation of R, F O Z over N. If F is symmetric, the absolute version versus the original, like non-absolute version, are going to be the same for Rademacher. So the thing that we're going to show is that if the class has VC dimension nu, then the Rademacher complexity is bounded by root nu over n. So in order to do this, to use the Dudley's integral, I have to define a process indexed by some index set or index. Yeah. So that's how I'm going to define it. So this is basically a rescaled Rademacher process indexed by a function. So if I plug in f, so as f varies in the f, that's the, let's say, loss class for us, then each one gives me a random variable. Okay, so basically the process is vf as f varies in capital F or script f. So it's a linear process in the sense that if I rescale f plus some g, I get alpha times vf plus vg. Okay, so what this is saying is basically that, let's say, v f minus, if I look at the increments, it's just basically v of f minus g. Okay, so I can simplify the notation a little bit by just considering the psi2 norm of vf, because if I control this in terms of the norm of vf, I'm basically controlling the deviations as well. This happens for the linear processes. The main point is that the psi2 norm, like the sub-Gaussian norm, is controlled like this. Now let's see if someone can argue why this is the case. So basically the psi2 norm is bounded by the so-called empirical norm. So all that the empirical norm is just basically this quantity. This is basically this, right? So this is the empirical, this is the empirical measure. EZ is the measure that puts mass 1 over n over the zi's. And so the L2 norm with respect to this measure is just basically this quantity that we have there. So what this is saying is that this process has sub-Gaussian coordinates and in fact sub-Gaussian increments with respect to this metric, the empirical L2 metric. So why is that inequality true? So basically I have to control the sub-Gaussian norm of 1 over root n summation epsilon I f zi. So what I'm trying to do here is, this is like conditioned. Conditioned on z. Like the only randomness here is epsilon. So psi2 norm condition on z. Yeah. Yes. No, standard deviation, not standard deviation, but like sub-Gaussian standard. Right. So this is going to be like, yeah, so this is going to be 1 over root n. It's a norm, so this comes out. You get this. You could treat these as like constants. So it's like having, so the problem reduces to controlling something like that. I have something like this, I from 1 to n. And epsilon i's are Rademacher, ai's are just constants. So how do you control the sub-Gaussian? So let's say square. So this would be sub-Gaussian norm squared is up to constant bounded by summation, if you recall. There's this property of sub-Gaussian norm or standard, which behaves like the variance for independent. So epsilon i's are independent. Independent sub-Gaussian, then this happens. And then again, because this is a norm, then I get AI squared comes out, right? So AI squared, and I get sub-Gaussian norm of epsilon I. So let me maybe take this out. Do a better job here. So this is what we are using here. So this is from this the independence. And then each one of these is bounded by a constant. So sub-Gaussian standard is bounded by 1, and then sub-Gaussian norm is within the like constant factor of sub-Gaussian standard. So up to a constant is bounded by 1. So this is going to be bounded further by summation I from 1 to n ai squared. So in other words, the psi2 norm, I like psi2 norm of this is bounded by the L2 norm of the vector A. Sorry, it's the L2 norm of this vector. Right? A is just A1 up to AN. Does that make sense? So just 1 over root n summation I from 1 to n epsilon I f z I. Psi2 norm is up to constants bounded by 1 over root n. Just root summation I from 1 to n f z I s squared, which is exactly this result that we have. So we have a sub-Gaussian process whose increments are controlled by the empirical norm, right? We're conditioning on z, so the empirical norm is some sort of a deterministic norm here. So we have this nice property, right? So what this is saying is that the expectation of the supremo of the process, so the expectation of the supremum over f of this vf by Dudley's integral is controlled by the root. So integral 0 to infinity root log the entropy number of the set f in metric, which is just the L2PZ, right? Okay. And what we showed there back in this result. So this is saying if I put any, so I have a Boolean class, if I put any probability measure on the space at Z, then I have the entropy number in L2 of P. I can just put the empirical measure there. that's a valid measure. And this is still holds, right? So the consequence of this is that, so condition on Z, PZ, the empirical measure, is a valid measure, valid probability measure. And so N epsilon F L2, yeah, sometimes I use this. I think this is the HTTP notation, but sometimes I put a norm, sometimes I put a space. It's a little better too. So I'm going to write it L2PZ is bounded by 2 epsilon C nu. Okay. Does that make sense? So I can just replace P with any measure. So I'm going to replace it with the empirical measure. So the end result is that this is, yeah, so this is upper bounded by, let's say, 2 epsilon C nu. So what I get is that when I take the log, sorry, the log of this, log. So if you take the log, so you get root C nu log 2 epsilon. And then there's the epsilon here. Right, so root C nu comes out. There is 1 over root n here as well. No, this is true. There's no root n here. So this is root, and then integral 0 to infinity root log 2 over epsilon d epsilon, right? What is this? This thing is going to be integrable because guess what? Just argue that this is a constant. The whole point is that this just is a finite integral. The upper bound, yeah. So yeah, we might have to do like, there is some sort of a big, I think probably it doesn't even matter. So this bound that we had only was valid for 0 to 1, if you recall, the way that we bounded it. Yeah, there's going to be some diameter there. Is it like going to be infinite as we go to infinity? It's like when epsilon goes to infinity. Right, okay, so yeah, probably we can, you're right. So I'm going to do this. You have to fix this, but at some point, this thing is going to be 0, right? So for sufficiently large epsilon, this is going to be 0. Yeah, just fix this like upper bound. So the key is when epsilon goes to 0, that's where it matters because it blows up, right? When we go to the other side, at some point, just the log would be 0. It's like the cardinality of the covering number. So the covering number just drops to 1, and the log would be 0. So just yeah, just figure out the upper bound. But the thing is that this is going to be a constant instead of paying the log, like some things just when the integral is going to be finite, and so it just turns out to be a number. And so this thing is going to be like further bounded by some root, some C prime nu. And then the actual Rademacher process, if you recall, this is basically like I'm going to put 1 over root n here, and then Rademacher FOZ root n. This piece is just supremum VF. If you supremum expectation over epsilon. So we put 1 over root n outside, and then 1 over root n inside. Then this piece is going to be this piece here is going to be this part. And then so I have another extra root 1 over root n here. So basically R F O Z. This already contains the expectation with respect to epsilon, but not z. So this is controlled by 1 over root n expectation supremum f in f vf. So this is further bounded by root mu over n. Okay, and then if I take the expectation over both sides of this with respect to z, basically, I get the same thing. At this point, I take the expectation with respect to z. This side doesn't depend on z, so I get this result. And this just goes back inside this tier. So I have a control over this, the expectation, which is root mu over n. Okay, so that sort of finalizes the thing. So now you can see how we define the process. Where does that index come in, right? So the index, in this case, you have a process indexed by a function class. And then once I restrict myself to z, basically you can think of it as you're passing to the subset fz1. This is the restricted subset, basically, right? FOZ. That's the set of all things that look like this. We're passing basically to this. If you think of it, it's just a process on teething this, if you want. But if you go through this argument, you can see exactly an example where the index set is non-trivial. So you can use the Dudley's integral to control the Rademacher complexity of the restriction of a function class to a set z, and then this bound is independent of z, conditioned on z, and then you take the expectation, so you also control the average Rademacher complexity. Okay, sounds good. Just let me just mention what we're going to do next. So now suppose I want to apply this with half spaces. So if I want to learn with half spaces, we can talk about why it's interesting to do learning with half spaces. Let's say consider binary classification with 0 or 1 loss. So I have a 1 bounded loss. These class of half spaces we saw by that sub-level VC dimension argument, that the VC dimension is at most d plus 1. And because the loss is 0, 1, I can just peel out that. So VC dimension of the loss class is bounded by the VC dimension of this, which is bounded by d plus 1. Okay. Then if I apply that result that we just proved, it says that if I do binary classification, like ERM, with 0, 1 loss and this set of half spaces, I would get an excess that looks like this. So the nu here is bounded by d plus 1 here. So I'm just replacing it with d up to constants. That's true. So this is saying that I can learn half spaces if I have more samples than d, basically. D over n goes to 0, which is fine, which is nice. But what if d is much larger than n? Okay, what if d, for example, is infinite? One question is that why do we care about half spaces in high dimensions or infinite spaces? I would suggest that you think about it. What would it be useful? The other thing is that suppose I want to do it with like infinite dimensional space. A lot of interesting things can be written as like infinite dimensional, a lot of functional spaces can be written as infinite dimensional Euclidean spaces, like Hilbert spaces, basically. So the question is that if I want to do it in infinite dimensional space, this bound is basically useless. Can we do like impose some conditions on the, this doesn't impose any condition on the P, the distribution X and Y, right? If I want to improve this, I have to, you can show, you may or may not prove that this cannot be improved if you like do, like don't assume anything on P. So for every estimator over this class, there exists a P distribution over X and Y such that X is at least root D over N. So you can't improve this. But if you impose more conditions, maybe we can just remove this D. Then it will be very interesting. So that's what we're going to do next.